Now let's actually do some problems from the book. Do some double integrals. We have this double integral of 4x plus 8y, where over some parallelogram r. We're going to go ahead and sketch that parallelogram, but we're going to use this transformation to actually compute the integral. So let's actually draw what we have. So I've got I'm going to graph the xy over here, then we're going to draw whatever the corresponding s. So r is going to be the region in the xy plane, s is going to be the region in the uv plane that actually maps to r. We go ahead and put in our vertices. R is just going to be a parallelogram. Let's make sure we're putting in the correct frame here. We had vertices of -1, 3, 1, -3, 3, -1, and 1, 5. We have this parallelogram here. I'll go ahead and connect those vertices. And let's actually zoom in on this. That's R. Obviously, that would be kind of annoying to actually integrate over, so we're not going to do that. We're going to figure out what it could be over here. Now, in order to do that, the best way of actually working this out is to actually figure out what these different boundary curves actually are. So if we derive what the lines are for this particular parallelogram, for one thing, we can note that this line here has a slope of 1. If we actually compute what its y-intercept is, it's going to be -4. Similar up here, this has a slope of 1 because they're parallel, and it actually does pass through the y-axis at 4. So those two lines are y equals x minus 4 and y equals x plus 4. If we go ahead and plug in these formulas for x and y, so y is 1/4 v minus 3u. That's going to equal x, which is 1/4 u plus v minus 4. And then you actually go ahead and solve that. You actually get that u equals 4. All the v stuff cancels out, and then we can actually solve for u pretty easily. So the line y equals x minus 4 is actually corresponds to the line u equals 4. Similarly, if you plug those formulas in for this equation, so this is plus 4 instead of minus 4, but everything else is the same. In fact, this time it just becomes u equals -4. We do the same thing with the other two lines. This line here has a slope of -3, and it passes through 0, 0, so it actually is y equals -3. Y equals -3x. This line over here also has a slope of -3. You have to actually figure out what its y-intercept is. It turns out it's 8. This line will actually go up here and hit at 8 somewhere. I'll leave it to you to derive those. Hopefully by this point you know how to do those algebra problems. But y equals -3x and y equals -3x plus 8. If you go ahead and plug these formulas in there, so y is again 1/4 v minus 3u. That's going to have to equal -3 times 1/4 u plus v. When you solve that, you get v equals 0. All the u stuff cancels out. Similar things here. So actually everything it stays the same, but we put a plus 8 at the end of it. And we go through all those steps. Of course, because we're essentially just bringing all this over here and everything simplifies to v, we get v equals 8. So what is that really saying? That means that our S is actually going to be a rectangle where U is going to go from -4 to 4, V is going to go from 0 to 8. If we go ahead and draw that in here, we can just go ahead and graph the points that we know are going to be on there. We have -4, 0. We have 4, 0. We have -4, 8. And positive 4, 8. And again, we can go ahead and connect those lines, or connect those points with lines. I don't know why it keeps wanting to deselect that tool. And it's being very inconsistent about it. And that is going to be S. It actually is a square, though that's not really too important. The important thing here is that it's a lot easier to integrate over this rectangle than it was over this parallelogram. But we can integrate over that instead of that. But we do need to actually compute the Jacobian. What is the Jacobian of this transformation? What is dxy over duv? Of course, we have to take the determinant of the partial derivatives. Remember, the first thing in here is going to be the partial derivative of x with respect to u. Since this is a linear equation, that's pretty easy to see that the derivative is going to be 1/4. Then we have the partial derivative of x with respect to v. What's the derivative of x with respect to v? It's also going to be 1/4 for the same reason. Then we have the partial derivative of y with respect to u. Well, the v here is first, so we're really looking at the u back here. We're going to have 1/4 times -3, so we have a -3/4. And then the partial derivative of y with respect to v, that's just going to be a 1/4. If we go ahead and essentially do our, what we could call it cross multiplication if you prefer. We have 1/4 times 1/4. Subtract a 1/4 times -3/4. Or in other words, we have 1/16 plus 3/16, or 4/16, which is 1/4. Our Jacobian is 1/4. That means our integral which I'm not sure if we'll have enough space on this page, but we'll at least start it on this page. So we're going to integrate. We're going to have to, well, we're going to be doing it over our u's and v's. So let's go ahead and put the v values first. So we're going to have the integral from 0 to 8, integral from -4 to 4. We're going to need to put our values in for x and y. So we have 4 times 1/4 u plus v plus 8 times 1/4 v minus 3u. That is going to be multiplied by our Jacobian of 1/4 du dv. And notice here, I make sure to put the u here so that my du is first. I could have swapped these and these just fine. Of course, we get to simplify everything that we have inside here as our first step. So, kind of why they have the 1/4 here is to deal with the 4 and the 8. But because we have the 1/4 here, we actually do get fractions inside. We're going to have a -5/4u plus a 3/4v. If we integrate with respect to u, this is going to turn into a -5/8 because we have to raise that power to a 2. But then we just have a 3/4 u times v. We go ahead and plug in our values, and I guess we'll do this on the next page. So we had -5/8. That's going to be times 4 squared, because we had u squared. Then we have plus 3/4 u is 4, then we have v, minus 5/8, but then we have negative 4 squared, so just 4 squared because the negative doesn't matter there, plus 3/4 times negative 4 times v, dv. Now, it turns out the negative 5/4 times 4 squared subtracted with a negative 5/4 times 4 squared, those actually cancel each other out. They're gone. The fact that the square got rid of our negative meant that none of that survives. So that's actually kind of nice. The 3/4 times 4 times v, that's really just going to be 3v. This part, we're actually going to get a negative 3v, but we're subtracting it. So we get a 3v plus 3v, or 6v. So actually, things simplified very nicely. Integral of 6v with respect to v is going to be a 3v squared. That's going from 0 to 8. That means we get to take 3 times 8 squared. 64 times 3 is 192. And that's our answer. That is actually the integral over this parallelogram of 4x plus 8y. And if we wanted to break this down into various triangles and stuff like that, we would get that same result. Okay, let's work on problem 18. Here we have another integral of x squared minus xy plus y squared, where R is the region bounded by an ellipse. So the x squared minus xy plus y squared equals 2. That's an ellipse. Let's go ahead and plot it. So x squared minus xy plus y squared equals 2. We have an ellipse. But it's not even an ellipse where its axes are parallel to the x and y axes. It's at an angle. This looks like something we wouldn't have much an idea of how to even tackle originally. In fact, where would you even break things down if you were wanting to work with this as a type 1 or type 2 region? How would you solve for x or y in that equation? None of those are easy questions. But it turns out with doing a transformation, in fact, the transformation they gave us here, it actually turns out things look very nice. It turns from something that looks very intimidating to something that's not too bad. So we need to figure out, what does this transformation do to the ellipse? So basically, what is x squared minus xy plus y squared if you change x and y using those formulas? Now that just means that we're just going to plug those into this equation. We're going to take square root of 2y, square root of 2u minus square root of 2/3 v squared, because that's what x is, minus that same thing times what we have for y is square root of 2u plus square root of 2/3 v. Then we add that same thing squared. Of course, we probably don't want to leave it in that form. Let's expand things out. Remember how we expand this out, we end up squaring square root of 2u, so we just get a 2u squared. Our middle term, we're going to multiply those two together, and we're going to multiply by 2. Of course, multiplying those two together, the square root of 2 here and the square root of 2 on top actually becomes a 2. So we end up with a minus 2 times 2 is 4. We still have the square root of 3 on the bottom. We have a u times v. Then we add this term squared, so we have a 2/3 v squared, and that's just this first part. Next, we take this part. Now, the fact that we have essentially the same thing, but with a minus sign here and a plus sign here, means that this turns into a difference of squares. We take the square of our first term here, so a 2u squared. Of course, we have this minus sign here, so we're subtracting that. Minus, or plus because of this minus sign, plus the square of our second term, so 2/3 v squared. This one we do exactly the same as we did here. In fact, we're going to get the same result, except instead of the minus sign here, we have a plus sign, so this minus sign turns into a plus sign. So we can have a plus 2u squared plus 4 over root 3 uv plus 2/3 v squared. Alright, let's simplify things. First thing we'll note, 4 over root 3 uv. This has a minus sign, this has a plus sign, but other than that, they're exactly the same thing. They cancel out. Very nice. Next we have, well, we have a minus 2u squared, we have a 2u squared, gone. Don't need them. So the only things that involve u anymore is a 2u squared. The ones that involve v, we have a v squared here, v squared here, v squared here. All those are times 2/3. We essentially get to add 2/3 to itself 3 times. Essentially, what is 3 times 2/3, or 2? We end up getting a plus 2v squared. In fact, I'm going to go ahead and factor out the 2. This thing here just simplifies to 2 times u squared plus v squared. In other words, this thing equaling 2 means that u squared plus v squared equals 1. Cancel out that 2. So if we go ahead and plot our boundary of S, we just have the unit circle. So we're essentially, instead of having to integrate over R, this ellipse here, we get to integrate over the unit circle. And that's actually going to be a lot nicer than what we were trying to do over here. Of course, we do need to know what our Jacobian is. We haven't done that part yet. So what is the Jacobian d of xy over d of uv? We're going to have to take a 2 by 2 determinant. Of course, our first thing here is going to be the derivative of x with respect to u. So that is going to leave us with a square root of 2. Then we take the derivative of x with respect to v. It's going to give us a negative square root of 2/3. Derivative of y with respect to u is square root of 2. Derivative of y with respect to v is square root of 2/3. When we cross multiply, essentially, square root of 2 times, actually, I'm just going to write it out. Square root of 2 times square root of 2/3 minus a negative, so plus square root of 2 times square root of 2/3. So 2 copies of the same thing. The square root of 2 and the square root of 2 on top here becomes a 2. So 2 copies of that 2, so 4 over square root 3. That's your Jacobian. Now, not all Jacobians are going to be constants. That's just happening in these first 2 examples. We won't have a constant for our next one. But the point here is to actually take our integral over that elliptical region of x squared minus xy plus y squared dA. We get to integrate over, I'm just going to write it as S for now. It's that unit circle. X squared minus xy plus y squared is actually 2u squared plus v squared. So we didn't just use this to figure out what the ellipse is, but it was also our integrand. So we get to make use of that fact again. And then we need to put in our Jacobian. Our Jacobian was 4 over root 3 du dv. Now, we are integrating over the unit circle. The unit circle is not a rectangle. It still seems like maybe kind of a tough order to actually do this directly. But there's actually nothing stopping us from using polar coordinates to evaluate this new integral. Since polar coordinates will work with circles very nicely, we can just go ahead and do that. It's just, in this case, u and v are going to play the role of x and y, which means that u squared plus v squared is going to be r squared. Since we're going over the unit circle, obviously we're going all the way around, so theta goes from 0 to 2 pi. R is going to go from 0 to 1. I already said here that u squared plus v squared is going to be r squared. We still have this 4 over root 3, that initial Jacobian, and now we need to put in the r from polar coordinates. Technically, it's another Jacobian that we're putting in here. Though if you want to, you can just keep continuing to think of it as just, it's something you put in when you move to polar coordinates. I'm going to go ahead and pull out, actually I'm going to pull out a 2 over root 3. I'm also going to realize that since there's no thetas involved here, this 2 pi can just be pulled out as a 2 pi. So we actually get a 4 pi over root 3 on the outside. Still taking the integral from 0 to 1. I left a 4 on the inside. Technically, we had a 2, and a 4. I left part of it inside because I've got r cubed. And r cubed is going to be very nice with that 4 there. This becomes r to the 4th. Going from 0 to 1. Of course, 0 in there doesn't give us anything. 1 gives us a 1. So we get 4 pi over root 3. That's our result. We integrated over an ellipse, something that may not have seemed possible in the first place. But once we have the ability to transform to another set of variables, it actually may not turn out to be too bad. Of course, finding that initial transformation might be the trickiest part. They actually gave that to us in the first place. You'd have to know how to do that. So I'm not going to say here that this is necessarily an easy thing to do. If I just gave you this integral, if I just gave you that integral to begin with and that ellipse, you'd have to think really long and hard to figure out a good way of tackling it. They just gave us a way that works out very nicely. And we kind of have to just roll with it until we have more experience with working with that kind of stuff. Our last example is problem 20. Here again, we want to take the double integral over some region. This time they gave us the boundary curves. I mean, they gave us the boundary curves last time. It was just the ellipse. But now our boundary curves are these 4 different curves. We have xy equals 1, xy equals 2, xy squared equals 1, and xy squared equals 2. So let's go ahead and plot those curves. So x times y equals 1 is a hyperbola, in fact. So is x times y equals 2. X times y squared equals 1 is not actually a hyperbola, but it looks pretty similar. And x times y squared equals 2 is another curve like that. So kind of looks really busy here, but really we're just concerned with stuff that's happening in our first quadrant. I do not want to move that. Here we go. So we're actually working with this region inside here. So it has 2 hyperbolas as its top, or I guess, no, these 2 are the hyperbolas. This one here and this one here, those are hyperbolas, and then we have these 2 that deal with the y squared part, are the top and bottom. Go ahead and label that. No, I want to move the R. There we go. It's this really kind of a thin, really stretched out piece that we want to integrate over. Now you can kind of already note, because u is equal to xy, xy equals 1 and xy equals 2 means that u is going to go from u equals 1 to u equals 2. Those are the two, what these 2 first curves turn into in the uv coordinates. Also, since v equals xy squared equals 1, xy squared equals 2, turn into v equals 1 and v equals 2. We can plot this, what we're going to be dealing with in the uv coordinates very easily. It's just going to be essentially a square, in fact. In fact, we can go ahead and zoom in here because it's going to be a lot smaller than what I originally had. If we go ahead and plot points 1, 1, 1, 1, 2, 2, 1, and 2, 2, and then connect these. Then we just have our S is that square. We're going to be integrating over that square in order to then essentially integrate over this really weirder shaped region. The integral over this weirder shaped region is going to be the integral over that square. We do need to figure out exactly what we're dealing with here, because what they've given us is u and v in terms of x and y. That's actually kind of the wrong direction. That is the inverse transformation. We want to express x and y in terms of u. So we're going to have to take those two equations and turn them around to get x and y in terms of u. And we need to do that before we can even discuss what the Jacobian should look like. So how are we going to do that? Well, we're going to have to play around with those two equations and see, can we cancel out everything except for y or everything except for an x? Well, if we take v and divide by u, what happens? We have xy squared divided by xy. That will cancel out an x, and it will cancel out one of the y's. So that will turn into a y. So y is actually v over u. The other one's going to be a little trickier, but what you could think of, why don't we square u so we have 2 copies of x and 2 copies of y, and then divide by v to get rid of 1 copy of x and 2 copies of y. In other words, u squared over v, if we write that out, it's x squared y squared over xy squared. The y's cancel out, we're left with 1 copy of x. Now you might not see that initially, but that's probably the easiest way to go about doing it. And once we have figured out x and y in terms of u and v, now we can compute our Jacobian. So the Jacobian dxy over duv, we're going to take the derivative of x with respect to u. So we're taking u squared over v, derivative with respect to u. Remember, the v on the bottom doesn't matter here, that's just a constant. So the derivative of u squared is 2u. So we have 2u over v. Now we differentiate x with respect to v. The u squared on top is a constant. How do we differentiate a v, a single v on the bottom? Well, that is v to the minus 1 power. When we differentiate it, we subtract 1 from that power. We actually get a v squared on the bottom, because a negative 1 becomes a negative 2. We still have the u squared, and we also need to multiply by that negative 1 power that we originally had. So we actually have a negative u squared over v squared. Next, we need to differentiate y with respect to u. Again, we have that negative 1 power, so we get a negative 1 over u squared for that, but we still have that v on the top. And then finally, the derivative of u with respect to v. Then now the u on the bottom is a constant. Differentiate v and get 1, so we just get a 1 over u. We get a cross multiply, so we get a 2u over v times a 1 over u minus a negative u squared over v squared times a negative v over u squared. Of course, here we have a u and a u on the bottom. Those cancel out. We end up getting a 2 over v. This one, those two minus signs cancel out. We still have that 1 minus sign there. The u squareds cancel out, and we cancel out one of the v's. So we end up getting a 1 over v. Or in other words, this turns into 1 over v. 2 minus 1 gives us a 1. So our Jacobian here is not a constant. We get to go ahead and do our integration. Remember here we're going to have to replace the y in the y squared. Going to use this v over u. So integral over r of y squared dv, or not dv, dA is the integral. Remember, our u and v are both going from 1 to 2. So the integral from 1 to 2, integral from 1 to 2 of y, which was v over u, or which direction it goes. Y squared is v over u squared. We need to multiply it by our Jacobian of 1 over v, du dv. Of course, this is v squared over u squared, but then we can cancel out one of those v's, so we get a v over u squared. The integral of, well, the v here on top doesn't matter when it comes to the du part. When we have 1 over u squared, the integral of that is going to be a negative 1 over u. Remember, when we differentiated 1 over u, we got negative 1 over u squared. We just had to shift where that negative sign goes. So we're going to have a negative v over u from u equals 1 to u equals 2. Or in other words, when we go ahead and put things in here, we're going to have negative v over 2 minus a negative, so plus a v over 1. So v minus v over 2 turns out to be a v over 2. Or maybe we write that as a 1/2 v. Integral of 1/2 v is going to be a 1/4 v squared. Still going from 1 to 2. Plug in 2, we get 1/4 of 4, so we get a 1, minus a 1/4 of 1, and so ultimately 3/4. That is the integral of y squared over this really weirdly shaped r. Alright, so hopefully that gives you a good idea of how all this stuff works. I mean, it is fairly complicated stuff. I'm not going to lie here. Being able to set this stuff up effectively can take some getting used to. That's why we actually spent time going over polar, cylindrical, and spherical by themselves, so we can actually make use of those without having to necessarily get into all this greater generality. But at least by this point, we have an idea of what is possible to do. So, if you have any questions about this kind of stuff, especially before our exams next week, please let me know. Send me an email, or you can visit me in my office hours. Either one of those is fine. But I'm going to stop this here, and I'll see you guys at the exams. So, see you guys.